night sky has always been a wonder to people. However, it has only been in the past few decades that we have truly begun to see the universe in all its glory. This is because we have only recently been able to look at the universe over the entire electromagnetic spectrum. Our universe contains objects that produce a vast range of radiation, with wavelengths either too short or too long for our eyes to see. Some astronomical objects emit mostly infrared radiation, others mostly visible light, and still others mostly ultraviolet radiation. What determines the type of electromagnetic radiation emitted by astronomical objects? The simple answer is temperature. Matter in space is made of molecules and atoms or particles that are in continuous vibration. The energy of the motions of this vibration is called heat. The hotter the matter, the more rapid the motion of the molecules or atoms. And temperature is just a measure of the average energy of those particles. Gamma rays are the product of the most energetic events in the universe. A number of different processes which were occurring in the universe would result in gamma ray emission. These processes included cosmic ray interactions with interstellar gas, supernova explosions, and interactions of energetic electrons with magnetic fields. Gamma rays that come from space are mostly absorbed by the Earth's atmosphere. Therefore, gamma ray astronomy could not develop until we could get our detectors above all or most of the atmosphere using balloons or spacecraft. The first gamma ray telescope carried into orbit on the Explorer 11 satellite in 1961 picked up just fewer than 100 cosmic gamma ray photons. These appeared to come from all directions in the universe, implying some sort of uniform gamma ray background. Such a background would be expected from the interaction of cosmic rays with gas found between the stars. In the late 1960s and early 1970s, the Vela satellite series were designed to detect flashes of gamma rays from nuclear bomb blasts. They began to record bursts of gamma rays, not from the vicinity of Earth, but from deep space. These gamma ray bursts, GRBs, can last for fractions of a second to minutes, popping off from unexpected directions, flickering, and then fading after briefly dominating the gamma ray sky. GRBs have been studied for over 25 years, with instruments on board a variety of satellites and space probes, including Soviet Veneta spacecraft, the Pioneer Venus orbiter, and the BATSE experiment on the Compton Gamma Ray Observatory. Where do these enigmatic high-energy flashes come from? For a while remained a mystery, turning on one of the most intense debates in modern astrophysics. This was settled in 1996, when the Bepo-SAC satellite pinpointed the location of a gamma-ray burst and discovered its X-ray afterglow coming from a distant galaxy. In November 2004, NASA launched the SWIFT satellite. Its primary mission is to detect and locate GRBs as quickly as possible, report the position of the burst, then follow up with other observations of that location in the X-ray, UV, and visual spectra. On April 13, 2010, NASA's SWIFT satellite recorded its 500th GRB. To continue the study of the universe in the gamma-ray spectrum, SWIFT currently operates in conjunction with the Agile satellite and the Fermi Gamma-Ray Space Telescope. Launched in 2008, Fermi, originally called GLAST, Gamma-Ray Large Area Space Telescope, also studies GRBs, as well as blazars, neutron stars, gamma-ray background radiation, supernova remnants, dark matter, and more. The International Gamma-Ray Astrophysics Laboratory, Integral, of the European Space Agency was successfully launched on October 17, 2002. It was lifted off from Baikonur in Kazakhstan on a Russian Proton launcher and is now on a 72-hour elliptical orbit ranging from 9,000 kilometers up to 155,000 kilometers from Earth. Integral played a crucial role in discovering the flash of gamma rays linked to the gravitational waves released by the collision of two neutron stars. On the 17th of August, Integral, as well as NASA's Fermi satellite, recorded a short gamma-ray burst. Such bursts are not uncommon, but this one was preceded a few seconds earlier by a gravitational wave signal. Gamma-ray observations would peer into the most extreme environments in the universe. Photons of these very high energies can only be produced by the interactions of subatomic particles that have been accelerated to almost the speed of light. The common feature of all gamma-ray sources is the non-thermal nature of the underlying emission processes, as opposed to thermal radiation that originates from the random movements of particles in matter. Non-thermal radiation may have a variety of origins. Decay or de-excitation of atomic nuclei, the decay of particles or their annihilation with antiparticles, and the interaction of non-thermal particle populations with photons and matter. Gamma-ray emission occurs in a surprisingly wide variety of astrophysical sources, close to black holes and neutron stars, in the blast waves of supernova explosions, and in the relativistic jets of active galaxies, or near to us in sun-solar flares, explosions, or even more, on Earth, at the top of our atmosphere. Gamma-ray emission might also result from the interactions of dark matter particles, and so provide a non-gravitational method to detect dark matter in the universe and to determine its nature. Gamma-ray astronomy presents unique opportunities to explore all these exotic objects. By exploring the universe at these high energies, scientists can search for new physics, testing theories and performing experiments which are not possible in Earth-bound laboratories. Gamma rays provide the clearest window into the non-thermal physics in our universe, and for decay, de-excitation, and annihilation processes, they often provide the only view. Understanding the nature of dark matter is certainly one of the most fundamental problems of modern science. The evidences of the missing mass at scales of galaxies, galaxy clusters, inevitably points us to a flaw in our understanding of nature. Gamma rays not only carry information about the cosmic ray intensity and spectrum, but also about the propagation physics. Gamma ray observations can be used to measure the cosmic ray energy density and to infer its spatial variations due to cosmic ray propagation. Astronomers are still looking for the first stars that had born in the universe, stars extremely huge, made of simple chemical elements named population 3 stars. They are an open issue in astrophysics and cosmology. These kinds of stars are expected to explode as a gamma-ray burst, GRB. The search and observation for GRBs in the X-ray and gamma-ray spectrum will show us their presence in the early universe, 13 billion years ago. By carrying out high-resolution spectroscopy of these objects with the Athena probe, we will observe the first black holes and the first metals produced in the universe. The observation of gravitational waves has opened a new way to understand and study the universe. Gamma-ray astronomy is the natural link between this new astronomy and the classic one. As in 2017, it's thanks to the use of gamma-ray telescopes that we were able to find the source of the gravitational waves.